Uh, yeah, so hello. I think we can start now. Probably the other session is finished now.
Yeah.
Okay, so then I will start with sharing my screen. There. Yeah. Yes. Hello, my name is Stefan Wiedemann, and I'm an architect at the FIWARE Foundation. Those that were at the last presentation probably know me as Ken's colleague that likes Java. But besides writing Mintaka, in the last months, I was also building scalable production-grade deployment scripts for running various FIWARE components, especially the Orion context broker. Besides providing those deployment scripts, we also wanted to provide a proof for the ability to scale and publish reliable numbers for that ability to scale. We solved that with a combination of Helm charts, leveraging on Kubernetes' ability to scale microservices, and some improvements on the context broker to get it more cloud ready. To prove those numbers, we used multiple open source tools for testing and publishing the results. In the next 30 minutes, I want to take a closer look on how to get started when building a scalable context broker deployment and an overview on our solution and how it can help you with your own deployments. Today's agenda will look as following. We will start with an overview and on what to analyze about your use cases and how this may impact your decisions. As second point, the infrastructure will be at focus. What should be taken into account when setting up such an environment? Third part, I will show some examples of possible optimizations that you can do. And after that, I will show our solution for testing the setups and the assumptions that were made. The last part will be a practical walk through the repositories that we provide for running the components. After that, I hope we have a little time left for questions, and I'm looking forward for your feedback. So the first task when starting to build a scalable deployment is that you should know about your use case. Most of the time in software development, we have to handle trade-offs. If you optimize one thing, it might degrade another one, or it does at least not scale in the same way. But in order to have every functionality at the same high level of performance, you probably need to oversize the installation in a way that it makes it expensive and inefficient to run. To prevent oversizing, I would always recommend to analyze the use case on the following aspects. Depending on your use case, there might be more, but those mentioned here are more or less applied to every use case. So first of all, you should decide on the core measurement that you want to optimize for. As you probably know, the LGSI-LD API, and therefore also the Orion broker, allows a wide variety of retrieval and querying operations and different methods to write data to it. Therefore, you should check if your focus is on very high frequent updates or if you're probably more focused on many parallel requests. The result of that analysis will help you to optimize the connection pool configurations and improve the efficiency of your overall setup. It also makes sense to think about the expectations that you have in terms of read versus write. If the typical request that comes into your broker is a complex query, you will put more pressure on the database, while a lot of parallel entity retrieval requests will put more focus on the broker's connection handling and might be the limiting factor. If your focus is on many parallel read operations or the mentioned complex queries, you have also options like an in-memory read replication for MongoDB that are not really useful if your focus is more on a lot of parallel write operations. It's clear that most of the time you will have a mixture of those, of all of those requests, but finding the focus and probably also the first functionality that will reach its limits might help you to get the right focus for the deployment. The next important point that we should look at is the kind of updates that we expect. The API allows different ways to update an entity, like full updates of single entities, updates of single attributes, or even updating multiple entities in a batch. If the use case requires a lot of parallel updates of single entities or attributes, the configuration of the connection pools for the broker and the connected database is very important. In case of fewer but bigger batch updates, you put more pressure on the broker's memory. Therefore, it's more helpful to assign more RAM to Orion instead of simply increasing the resources for MongoDB. Another important thing to look at is the kind of features that you are using. In NGS-ILD, subscriptions are a quite important and powerful feature, but it's also a feature that can easily harm the performance of the broker if you not correctly use them or configure them properly. So first of all, you should check if you need them. If they are used, it's important to know how the typical subscription will look like. If there are a lot of subscribers only receiving some data each, the connection pool configuration should be different than if you only have one or few subscribers, like, for example, deployments where you use additional components like Quantum Leap or Cosmos. Orion provides very fine-grained options for configuring the connection pool that can make a huge difference for any given scenario. I will not talk too much about those options, but I can recommend you to take a close look on the documentation for them when optimizing the broker's deployment. I linked the Orion performance tuning manual down here. The last important point for the subscriptions is that you should be aware of the impact that the subscriber's performance has on the broker. If a certain subscriber is very slow or even unstable, it can also slow down the broker itself. In such cases, it might make sense to use some kind of a circuit breaker on the cluster to allow a fail-fast for the notifications, or put, for example, a more stable and performant intermediate component like an MQTT broker in front of the subscribers and use MQTT subscriptions. Another interesting but also impactful feature is the temporal representation of entities. Starting with Orion versus version 1.0.070, the broker supports the NGS-ILD temporal API. To work, it requires a timescale DB as a backend and therefore additional resources. If you don't need historic data, I would recommend to simply disable this feature. If you need it, you should decide if you need the full history for every entity, or if you are more interested in only a small subset, even maybe with a reduced density. If that's the case, you should compare the impact of temporal representations to other options like using Quantum Leap, for example, via subscriptions. Additionally, the size of the database will have an impact over the time because clearly, if you use the temporal representation, the database will continue to grow. You should think about stuff like data retention or downsampling to reduce the overall amount of data inside the database. Maybe even move some of the data into another database that you use for long-time analysis at some point. I will not dig much deeper into that, but you should check the documentation of timescale DB for those options. Okay, now that we know how a use case looks like, we can start with a little optimization. In order to do that, we not only need to take care about the broker itself, but also about the underlying infrastructure. It's very nice to have a setup that has the ability to serve tens of thousands of requests a second on a benchmark, but it can be a little terrifying if you do not have the infrastructure to manage and operate it in a production environment. Since the overall infrastructure should fit with your other operational needs, I will not recommend a specific installation, but give an overview on the problems to be solved and how we do it in our environments. The infrastructure itself needs to be able to scale with the use case and also support managing a highly scaled cluster, especially in the peak situations. To fulfill such requirements, we need a high degree of automation. Therefore, we choose Kubernetes as the recommended orchestration tool for installing the FIWARE components. Kubernetes was originally designed by Google and is now an open source project maintained by the Cloud Native Computing Foundation. Therefore, Kubernetes can be run on bare metal systems, but is also offered as a managed service by most of the cloud providers. Our internal clusters use OpenShift 4.6 on top of the Google Cloud Platform. This provides us with an abstraction layer to use the same deployment scripts in different environments. Besides that, it has functionality for automatic up and down scaling, thus can help with building the cluster in a very cost-efficient way. An important but often overlooked point in high-load scenarios is the ability to update the installation to new versions. Under such loads, it's often not feasible to simply turn off the broker and replace it with a new version. Therefore, the system needs to support rolling updates so that you can gradually replace the running broker without stacking up too many pending requests. Kubernetes provides a lot of options for that. I would recommend you to read the documentation on it before you start with a production setup. And since every deployment of the broker also needs some degree of individual configuration, we decided to use Helm charts for the deployment script. Helm is another CNCF project and provides templating mechanism for Kubernetes recipes. You can find the chart for the Orion link for the Orion broker, for example, at this link. In the last part of the presentation, I will give a short overview on this repository. Besides those deployment scripts, I would recommend putting some focus on the operational tooling. Running and being able to react on a cluster and high-load scenarios requires proper support for logging, monitoring, and alerting. The tools providing that functionality should integrate into the overall cluster and workflows and should be able to handle those high amounts of operational data that can occur in such environments. Especially in error cases, it's very common that the log infrastructure gets flooded with a lot of messages. As mentioned, our own clusters are built on OpenShift, and OpenShift already provides us with those functionalities. If your cluster does not provide this out of the box, I would recommend taking a look at some of the more mature and common projects like Prometheus, Thanos, and Grafana for monitoring, or the Elastic Stack for logging. Additionally, if you run your cluster on a certain cloud provider or one of the hyperscalers, they often already provide some managed tooling for that. You should carefully calculate if this is beneficiary because it can become expensive. Since the ingress controller also will receive the same load as Orion, you should make sure that it can scale in the same way as the broker and that it might support other operational aspects like, for example, monitoring the golden signals. We use HA proxy and Nginx in our cluster, but I think that other common controllers like Grafik or Contour are also sufficient. And as a last point, you should be aware of the disks for the used for the databases. Both will benefit from using SSDs, but especially for historical data, the higher price tag should be taken into account, and it might make sense to use HDDs there. Okay, now let's take a look at some of the optimization options. If the analysis showed that we have a need for high write performance, we can do a couple of things. The first thing that I would recommend in any setup is setting an index on ID. This might sound counterintuitive since indexes usually decrease write performance, but Orion always retrieves the entity from the database before writing an update and therefore greatly benefits from this index. If you're running MongoDB yourself instead of using a managed offering, you should definitely use SSDs on MongoDB. This will drastically increase the write performance. As you probably already see, Orion's performance is very much dependent on the performance of the MongoDB. In general, a single replica of Mongo requires about 2 times the CPU as Orion, which sums up to 4 times the resources if you factor in replication. Therefore, it's important to know how to scale Mongo to properly with Orion. Especially for write scenarios, I would recommend to scale Mongo vertically by adding more resources to each individual replica. Our setups currently use a replication of 2. You need to decide for your use case if that's enough or if your availability requirement is higher than that. Sharding for Mongo should only be used if you don't have any options for vertical scaling left anymore, since the NGSILD data model does not provide us a natural sharding key that ensures equal distribution of the entities through the shards. Therefore, we have to use a hash key, and our tests showed that the hashing did reduce the overall performance basically back to the same level as it was with vertical scaling. Thus, the additional complexity of sharding should be avoided, in my opinion. It can be an option, so sharding can be an option if the use case does provide you a sufficient key. For example, if you have some geolocations that distribute equally. Batch operations also does provide an interesting solution in some scenarios, for example, IoT gateways. If you're trying to optimize for that, you should assign additional memory to Orion, since Orion becomes susceptible to out-of-memory kills in some edge situations. If your analysis came to the conclusion that read performance is your main focus, the easiest improvement is also to use indexing. You should review your data model and the expected queries that you have and set indexes that optimize exactly for those queries. Another option is the usage of read replicas. In Mongo, a replica set has one replica that is responsible for writing. I have it here in this small diagram. But every of the replicas can serve the read requests. If you have enough memory assigned to the instances of MongoDB, it can basically hold the whole database in memory and serve it without any serve the read requests without any I/O operations involved, and therefore can further increase the read performance. If you can see here, so we have basically the MongoDB master node, which is handling all the write operations, and the other replicas replicate from this master node, and all three of them can serve the read operations. If you are using the enterprise version of MongoDB or even some managed Atlas instance, you also can take a look into the in-memory engine of MongoDB. MongoDB usually uses WireTiger, which is writing to disk, but there is an in-memory engine that holds everything in memory, even without any persistence. And if you assign this to specific read replicas, you can further increase the performance on read operations. Okay, after analyzing the use cases and setting up the infrastructure and the broker itself, all the assumptions and decisions that were made should also be tested. In order to do that, we implemented a set of load tests that can be run against any implementation of NGSI-LD or the NGSI v2 API, and allow the test if it's able to handle blend load and find the boundaries of the implemented installation. The tests are built based on the Gatling framework. Gatling is an open source framework for load testing that supports a high degree of parallelism and offers a domain-specific language to implement relatively easy to read tests in Scala. It provides reports that allow close analysis of the test runs and configuration mechanisms to run the scenarios in different sizes. The reports that are provided in HTML and look similar to the ones that you can see down here. You will see more than on the repository walkthrough. Our test implementations are fully available on GitHub, and you can execute them via Maven or inside the Kubernetes cluster with a Helm chart. For simulating high load scenarios, running via Kubernetes is recommended. The Gatling scenarios will then be scaled out over multiple pods by the chart and report to a central instance inside the cluster that then aggregates the reports and finally reports the overall report. Beside that, if the tests are run inside the cluster, you take away the network of the load generator as a potential bottleneck. But you should also be aware that the external load balancers and, as already mentioned, the ingress controller need to be able to handle load too. The tests will then only go through the internal load balancing. Besides the test implementation itself, the GitHub repository also offers reports on test runs that we executed. The tests were run on different sizes and configurations of the cluster and should provide you a reference for choosing the right size of your cluster. All reports include a detailed description on the configuration of the infrastructure and the charts that we use for Orion, MongoDB, and timescale. We also provide all the configurations that we use there because Orion is tightly coupled to its databases, and therefore both need to be scaled in order to not become the bottleneck. So now let's take a short look on the repositories. We will start with the Helm chart repository. I hope this is big enough. We provide in this folder a couple of Helm charts for different FIWARE components like API Umbrella, some business API ecosystem stuff, IoT Agent, Keyrock, Mitaka, and Orion, which is the focus of this presentation. The Orion chart is basically compliant to the Helm best practices, so not much special here. We have a values file with some default values that you can use to play around. But if you want a really performant installation, you should take a look at the Orion load test repository first. But I will show that in the next step. We also provide this repository as a Helm repository, as you can see here, so that you can install all the charts directly from the Helm repository. It's also listed on Artifact Hubs if you want to search it, and we have some kind of chart linting available. The second repository that is interesting to use together with the Helm charts is the FIWARE Orion load test repository. It starts with the description of the whole framework at the start page, and as already mentioned, you can run the tests with using Maven or with Helm. Since all of those tests are normal Gatling implementations, you can also use any other way that a Gatling test can be run. You should probably look at the Gatling documentation if those options don't fit your needs. Down here, you can find detailed implementations on all the tests that we implemented. They are focusing on the most common use cases of the NGSI API. If you have discovered more specific scenarios in your use cases, it might make sense to implement an additional test for yourself. The first set of tests focuses on write operations. We have tests for single entity retrieval, and we also have tests for single entity updates, and also some for batch updates. The parameters that you can configure are always described below the test documentation. I will show the configuration file later. Another group of tests is focused on read scenarios. We have tests for single entity retrieval, and we have also tests for querying of the wiring complexity. Since we need a data set to query on for those tests, we create a sample scenario on start of every test and clean up this scenario afterwards. You can find more about the use scenario inside the documentations folder. It's here. So you can see we create entities of type store, owner, product, and inventory, and link each other using relationships, and all of them have some kind of properties. How they are directly connected and how they are queried can be seen inside the test implementations. Let's go back to the first page. What's also interesting is that all of the tests do support a prefill parameter that you can find in the test configuration. The prefill can be creates a certain number of entities before the test starts and puts it into the database, so that you can see how your database, how your performance will evolve over time when the database already is filled up to a certain degree. This test configuration file can be used for configuring local runs, for example, via Maven or via other Gatling tools. You can find the documentation for all these configurations on the starting page. The Helm chart of the tests also allows you those configurations in the values file. You can find them here. They are then automatically set for each test run. Let's go back. Because we have a third group of tests that you can find here. It's kind of an extension to the update tests that focuses mostly on notifications. It will create the same Gatling reports as the other tests, but it will also provide some measurements on the duration it takes from an update generated at client side until it's received by its subscriber. In order to take out the subscriber as a potential bottleneck, as already explained, we use in this case Telegraph and InfluxDB and give them quite a lot of resources so that they are able to handle all the load. As shown here, we create a timestamp when the entity is generated at the Gatling client, and then we create a received timestamp when the notification about the update is received by Telegraph. And then we store all reports inside InfluxDB, and they can be analyzed using Grafana. Okay, so as advertised, we provide reports of load tests that we did run ourselves, and you can find all the reports inside the test reports folder. As you can see here, we currently did test two different kind of setups. One with Orion and the temporal operations disabled, so we only have Orion and MongoDB here, and we have another one with Orion and temporal operations enabled here. There is a short overview on the difference that it makes for temporal operations enabled versus disabled in terms of the update performance of Orion, so that it has a first indication. You should definitely look at the subfolders for more detailed results. Right now, we tested installations of 3 different sizes, focusing only on the broker and its connected databases. We call the environments currently tiny, small, and mid, scaling from 9 CPUs and 22 GB RAM on the tiny installation up to 9 CPUs, up to 38 CPUs and 96 GB RAM on the mid installation without timescale, and from 13 CPUs and 38 GB RAM up to 54 CPUs and 160 GB RAM on the installation with timescale enabled. Let's go back to the Orion repository, Orion report. Be aware that in a complete production cluster, you will need more resources because we did not include load balancing, monitoring, alerting, logging, and so on in here. You will also have resources assigned to master nodes, for example. But now let's take a look at the concrete setup. I will start with the tiny one. As you can see, the Orion LD broker is able to handle around 1,800 updates per second on the NGSI LD endpoint with only one core, and also a retrieval of about 4,200 requests a second. With temporal activated, you can this update number goes down to about 1,400 requests per second. In the temporal tests, we do not include numbers on retrieval yet, because as Ken already mentioned, this is the temporal retrieval is handled by another component called Mintaka that we have no load tests yet. Be aware that those numbers might change from time to time, and Ken is working a lot on the improvements for this. The detailed reports on any tests that were described in the beginning can be found here. We can look at this one, for example. You can find information about the average request time on top of this page. For example, we can see that 15,000 of these requests were answered in less than 800 milliseconds, that close to 20,000 needed more than 1.2 seconds, which is expectable because we have subscriptions enabled for each of those updates. In the table below, you can find more detailed information on every test, on every step of the test, so how long it took to create the entities, or how long the individual attribute updates took. You should not get confused about the notion of active users in this report. That's the standard naming from Gatling. In our case, user corresponds with entity. Then you can see a lot of different graphs that show detailed information on requests and response timings. You should check which one is most interesting for you. In my opinion, the last one is the most interesting because it will help us find out the boundaries of the system. The graph shows the number of parallel responses per second. And as you can see in this graph, we have kind of a plateau in the middle because the beginning is the ramp-up phase where all the entities were created. And in the end, we have the tear-down phase where everything is deleted again. So this is basically the region where we have the continuous updates coming in. And we can see that we have around 800 to 900 responses per second in this environment for updates with subscriptions enabled. Okay. Additionally, for the tests that with measuring notification latency, we also publish an image of the used Grafana chart. You can see that we had a mean latency of 1.3 seconds in this case. More detailed analysis for the latency should be done when you run the clusters, the tests on your own cluster, because it requires an active InfluxDB. If you have higher load scenarios, you should take a look at the small and mid setups that you can find here, where we can go up to 12,000 updates per second, for example, in the mid setup with temporal operations disabled. As you can see, we observed nearly linear scaling for Orion here. We also did run some tests on an environment twice as big as the current mid, which will be called large in the future. We did still see linear scaling there with far above 20,000 requests per second, but not all tests were run on this cluster yet, so the numbers will be published in the next couple of weeks. Another interesting report is one that we did for one of the tenders that we had. It's called Entity Updates Long. We only run it on the mid environment yet. And we needed to show the ability to handle millions of data points over the span of a day. So we did let run the tests for about 4 hours. And as you can see, we were able to reach above 96 million updates in this time frame. 85 million of them were answered in less than 800 milliseconds, and another 10 million between 800 and 1,200 milliseconds. As you can see down here, it's a very steady curve that we have. It was with an older version of Orion, as you can see, because we only have 9,000 requests here. With the latest version, you can go up to 12,000 with the same. We actually were not able to go beyond the 4 hours yet, because the resources that were assigned to the test framework's result aggregator were exhausted by the amount of test data that we generated. So we probably will do a rerun in the future. In addition to those test results, we also provide the information on how to reach it. You can find this here, as already mentioned, our clusters run on OpenShift. You can find detailed information about the machines that we use, and also all the Helm commands that you need to set up such an environment. You can also find here on how to set the mentioned indexes in order to get the expected results. The values of the MongoDB and also of Orion, and in the temporal operations case, maybe let's go there. You can also find the information for the timescale database are provided as Helm values files in the config folder. You can see here. So if you use them with Mongo, you can get the same results. We also provide the definition of an SSC storage class, but this will only work on the Google Kubernetes engine, on the Google Cloud engine, and needs to be adapted for the concrete environment that you're running in. Okay, so I hope this will give you a good starting point for your Broker installation. Thank you for listening. Yeah, do we have questions? I can take a look at the question and answer session, but I think Ken already answered the one that we have there. Are there any additional questions or remarks? Yes, there are actually plans to check the performance of the other components and brokers. So I will work on extending this, the whole setup with an API umbrella and some integration with Keycloak in the future. And I also would like to test this with the other brokers like Scorpion, Stelio. I will probably also get in contact with you, Martin, about this, because it takes a little time in configuring the setup properly so that the numbers are good. So if we took the naive approach with Orion in the beginning and we had ridiculously bad numbers, so it wouldn't be a fair comparison without any work into the setup. So yes, I would like to test the other brokers, but I might need help from your team for this to get comparable numbers.
Okay, I had a comment. Stefan often says, and even writes, Orion, but he really means Orion LD. Because all these tests that he has presented are from Orion LD.
Yeah, that's true. Right? Yes, that's true. The Helm chart plot can also be used for Orion.
Yes.
Okay, so if nothing else is there, we probably can end this session. I will be available in the lunch for additional questions. Okay, then yeah, goodbye and have fun in the next sessions.
Thank you everyone for joining.
Yes.
The next session will start in 5 minutes, so see you there.
Let me see if I can quickly